In operational cargo inspection, screeners work within a strict constraint. They have roughly 1 minute to detect shielded, high-Z nuclear materials inside a sealed container. Probing these volumes without physical intrusion requires a specific type of radiation. That tool is muon scattering tomography. When cosmic rays strike Earth's atmosphere, they generate a constant flux of muons, heavy particles that arrive at sea level at a rate of 10,000 per square meter every minute. These particles possess enough energy to penetrate several meters of dense lead or steel. This schematic illustrates the mechanics of the Highland formula. When a muon traverses a material, it undergoes multiple Coulomb scattering. The root mean square scattering angle is inversely proportional to the square root of the material's radiation length. Materials with a high atomic number, or high Z, have shorter radiation lengths, which forces the muons to deflect at wider angles. This physical correlation makes muons uniquely sensitive to heavy elements like uranium, but their effectiveness in the field depends entirely on the precision of the trajectory reconstruction algorithm used to map the scattering events. For decades, the industry standard has been the point of closest approach, or POCA. It relies on a basic geometric assumption. The algorithm takes the incoming and outgoing tracks, extrapolates them as straight lines, and identifies the single point of closest intersection as the scattering location. This method causes a massive loss of data. By depositing the scattering signal at a single geometric point rather than across the physical volume, POCA recovers a maximum of 34% of the true material density. This geometric assumption also creates a vulnerability to shadowing. When two dense objects overlap along a muon's path, the single vertex assumption fails. The algorithm often places the scattering point in empty space between the objects, failing to resolve the actual material boundaries. Because POCA calculates every muon event in isolation and discards global physical context, it cannot reliably see through shielded environments. Overcoming these limits requires a neural network capable of reasoning about the physics of the entire volume. MuonPathNet was developed to address these failures through a progressive series of physics-informed neural networks. It intervenes at the event level, predicting physically plausible trajectories before any voxelization occurs. The first iteration, V1, establishes a baseline. It feeds a 13-dimensional observation vector into a 3-block multi-layer perceptron. V1 predicts discrete waypoints along the muon's path, acting as a generic regression model without specific physical priors. While V1 proves that a network can learn a basic mapping using mean-squared error, the unconstrained output space allows for physical impossibilities. Predicted trajectories often curve erratically through open air, violating the straight-line propagation of particles. To achieve a reconstruction that works in shielded environments, the laws of physics must be embedded directly into the network's architecture. Model V2 embeds the single scattering approximation as a rigid architectural bias. This simplifies the task, moving from complex waypoint regression to precise vertex localization. The V2 panel shows an upgraded structure, a 6-block prenormalization residual backbone processing features in a 256-dimensional space. The data flows into two specialized heads. The fraction head strictly confines the predicted scattering point within the measured volume. V2 also introduces an angle-weighted composite loss function. It uses a sigmoid weighting factor that increases based on the measured scattering angle of each individual muon. Since high-Z materials cause wider deflections, the network is rewarded for correctly localizing the muons that provide the most tomographic evidence. Reformulating the physical model as an inductive bias, rather than a soft suggestion, significantly improves the contrast of the reconstructed material. But muon datasets often contain catastrophic outliers, muons that scatter multiple times or encounter detector noise, which can destabilize training. Model V3 addresses this by removing the fraction head and switching to a Huber robust loss. It also implements a 2-stage angle weighting system capped at 20x, preventing extreme outliers from generating massive weights and severe overfitting. This robust loss formulation allows the network to maintain stable gradient dynamics even when the input data is severely degraded. The V4 architecture introduces a different strategy. Rather than predicting absolute coordinates, the network learns a residual correction relative to a physics-derived anchor point. This is achieved through a dual-stream architecture. The input is separated into a trajectory stream for raw observations and a physics stream dedicated to geometric features. The logic is defined by the residual equation, V equals A plus delta V. The physics stream establishes a geometrically grounded anchor, and the network only needs to predict the small correction needed to find the true scattering vertex. For complex anchors, V4 introduces the spline processor, a specialized module that treats muon paths as continuous sequences rather than unstructured data. The spline processor runs 1D convolutions across 5 points sampled along a curved spline path. This design allows the network to capture the curvature and smoothness of the trajectory. Standard linear layers destroy this spatial geometry by flattening coordinates into a single vector. The spline processor preserves the physical continuity of the path. This residual anchor approach balances the two extremes. It avoids the sparse, underfilled maps of geometric models without the signal dilution seen in unconstrained neural baselines. To test these models for the real world, researchers subjected them to Scenario 3, severe shadowing. In this setup, objects occlude one another, making it nearly impossible for standard geometric models to locate the scattering source. This radar chart compares models in this extreme environment. Traditional baselines plateau, failing to recover occluded signals, resulting in low structural similarity. Yet MuonPathNet v2 emerges as the most balanced. Its blue dashed line sits on the outer edge, maintaining quality when data is thinnest. While v4 provides maximum fidelity in ideal conditions, the robust architectural bias of v2 delivers the most resilient performance when data is deprived by heavy shadowing. These systems are built for cargo screening, where every muon event must be processed in real time. The computational complexity scales with the architecture. The v1 baseline is extremely lightweight, while the v4 models utilize roughly 1.3 million parameters. This chart highlights the throughput trade-off. v4 with the spline processor offers the highest structural similarity but lower speed. v2 offers comparable signal accuracy while maintaining 4.3 times higher throughput. Despite these differences, even the slowest MuonPathNet variant can process a full 600,000 event dataset in under 2 seconds, well within the 1-minute screening requirement. In a blind detection test, the models were asked to find sugar concealed inside cigarette cartons. Without any specific training for this scenario, the networks accurately reconstructed the voxel grid, proving the learned representations captured transferable physical structures rather than simple dataset correlations. By embedding physics-informed priors directly at the event level, MuonPathNet achieves signal recovery ratios near 1.0. This effectively solves the density underestimation problem of traditional methods, providing a reliable pathway for the real-time screening of shielded nuclear materials.